scene classification images in order to monitor the cloud profile of the different regions. Different Sentinel-2 tiles have taken into consideration in order to take images all over the area across Lithuania territory. Moreover, Sentinel-1 images encapsulate 2, taking into account the backscatter coefficient and coherence coefficients. Since Sentinel-1 measurements are able to penetrate the clouds and provide frequently and with stable resolution, with stable time frequency, some imagery. Also, some auxiliary metrics have been devised, like mixed coherence, radar vegetation index, the ratio between the components, and some differences. Something interesting that we have to take also into account for the training of the total routine, some of the clouds have not been masked properly, so some auxiliary algorithms have been devised in order to eliminate cases of some sudden drops that are not matched with some mowing event. Another another approach will be the usage of other masks like Maya or F-mask or S2 cloudless. Moreover, the construction of a more compact and appropriate temporal system common for all the areas would be important in order to match every observation taken into account with some other date, in order to have the same date that we have that we evaluate the events and the creation of the new artificially NDVI. So we have taken the dates of the Sentinel-1 orbit 131 in order to have this common temporal system of reference. Moreover, we have made some analysis for the cloud coverage across the different areas studied in order to depict the total cloud profile of all the Lithuanian region. As we can see, each region has its own cloud profile, and as a result, this is really important in order to create a model that is generalizable across the whole Lithuanian territory. Also, it's interesting that we are working on a pixel level in order to enhance our performance and resolution, since more pixels give us the ability to work with more instances to train our routines. In order to validate now the cases that we are we have into our dataset, we have created some extra masks of 0-1 in order to artificially hide some time steps of some dense NDVI time series that we have collected. According to the profiles I've showed you here, in order to match with some more realistic scenarios for the Lithuanian case. As a result, we can create a model that is fully directed to Lithuania cloud distribution, and handle better the problem of cloud coverage. Here, the problem is to deal with large gaps and steep drops that common interpolation methodology will not have the ability to cope with. For that reason, we are taking into account the Sentinel-1 images that I informed you previously, and the available Sentinel-2 observations. And as we can see here in this example, the time series that we can create now are more close to the actual ground truth, and something that we have catch these sudden drops, something that we would have missed it in case that we have used some common and very baseline interpolation methodologies like linear interpolation, for example. As a result, we can have better performance on the events identification. Our model is based on a deep learning architecture. It is composed from two individual components of a CNN, of a convolutional neural network, and an RNN of a recurrent neural network, in order to create this NDVI time series of a constant time step. The inputs are the Sentinel-1 images and the available Sentinel-2 observations as well. And now we can see some visualization that the model takes the Sentinel-1, for example, observations and the available Sentinel-2 and create the new NDVI output. We can see that we can catch the drops of the NDVI and also create smoother time series and ignore some observations that are cloudy and potentially create the problem of false events identification. The results now are quite well in comparison to some common interpolation methodologies. We can see that the error between the actual observation and the predicted value is far better in comparison to these methodologies, and across each region individually. So we have some generalization of our methodology. Also, we have a quite good correlation between these values, and the sparse for the different level of sparsities, the performance of Sentinel fusion routine, the creation of the new NDVI time series, is better, since we are working with different level of sparsities as well. Also some level of performance for the different time steps, for the different acquisition days. And we can see that as it is expected, the error is becoming a bit higher on dates that we have more NDVI drops below than 0.5 of the NDVI. This is expected since these values correspond to sudden drops that is not always easy to catch. Also, some tests about the generalization of the model. Here we perform tests using as training only, for example, the region 1, the region 2, or the region 3, etc. as well. And we evaluate the performance of the rest of the regions. And we can see that in almost all the cases that the results are quite similar and good. For the validation now, we perform some photo interpretation campaign using the indications from the NMA, the paying agency of Lithuania, and Sen4CAP predictions. So actually, we use the most confident Sen4CAP predictions in order to go to cases that we have for sure some mowing events. So we have our labels now, and we are moving on to how this Sentinel-1, Sentinel-2 fusion routine is able to provide some more accurate mowing detection products. We have two different approaches. The approach of Zwitter and De Vrij. Actually, De Vrij is the algorithm used by Sen4CAP. And we use only the Sentinel-2 component in order to have some more appropriate, some fair a more fair comparison, since we are taking into account only Sentinel-2 components. And we can see that the results are coming much better if we use the Sentinel Fusion time series in comparison to use the raw data or some other interpolation methodology. Also, the most important stuff is that we have managed to improve the performance for the high sparsity scenarios, cases that the cloud observation are very, very frequent. So as we can see here in the table below, in the second table, we can see that even for sparsities of above 0.5 or 0.6, practically time series that are almost empty, we managed to catch a lot of, to identify the majority of the moving events. Some other tests that we have performed is that we artificially hide the moving events from the time series, and we try to see if we are able to detect the events using our Sentinel Fusion routines. And as we can see here, we managed to recall, to identify, recall is the ground truth that the percentage of the ground truth that we have collected. We managed to identify the majority of these events. Also, precision is very good. With precision means the percentage of what is the percentage of the correct predictions that we have identified. So we can see that we have also quite well level of precision in our routines. This routine is, as I said before, is a pixel-based routine, so we can perform an analysis for each pixel individually. Moreover, we can use the same architecture of Sentinel Fusion in order to perform a moving identification task, not only some threshold-based routine like the Sen4Cap algorithm or the feeder methodology. And we can see that our routine, deep learning routine, is able to improve even better the performance and identify more cases. Also, since it's pixel-based, we can, as I said before, we can identify products. We can identify a prediction for each pixel individually, and at the end, aggregate the results at the parcel level. This product is really important in order to monitor the grassland management activity and provide some more ecosystematic aspect. This is another aspect of our product. How we can see the management activity, how we can evaluate the management activity of the total country. This is a national scale product, and we can move on to the identification of compliance. If at least, for example, in the case of Lithuania, an event happened until the 1st of August, for the majority of cases, of course. And we can provide a map for the compliance if these cases agree to the national regulations or not. To sum up, this is a pixel-wise routine that can create an NDVI time series that integrates both Sentinel-1 and Sentinel-2 acquisition. And it is a deep learning approach that is based on recurrent neural networks. Moreover, meteorological data maybe will be taken into account in order to ameliorate our results, or some more sophisticated architectures based on the latest developments of artificial intelligence. It is very useful since we can analyze the grassland management activity of a country and provide an eco-scheme knowledge. Also, this routine can be generalized to a variety of similar event identification tasks, like, for example, stable burning identification, since the nature of the problem is similar. We have again some time series that we want to identify sudden drops. This year also we have faced the problem of Sentinel-1B anomaly that occurred in 2021. So in order to cope with these situations, we have taken into account more Sentinel-1A orbits. And our methodology have been presented also to some symposiums and review meetings with quite success. And we are very happy for that. So thank you very much. Thanasis, would you like to move on with the presentation of DataCube?
Yes, Anas, thank
Thank
you
you
very
very
much.
much.
Just give me a minute to share my screen. Okay, can you see my screen?
Yeah.
Yes.
Yes, thank you. My name is Thanas Trivas. I'm research associate at National Observatory of Athens in Beyond Center of Excellence. I'm the responsible for the backend processes regarding the ENVISION project. So what we are going to see today is related to analytics functionalities and some specific services we provide during this project. And of course, how users can access these services and products beyond the ENVISION platform that already exists, but in other ways also. Before I start, I have to mention the core module of our solution, which is the data cube. And what we mean by data cube is multi-dimensional arrays. So they have also the spatial information, but they have also other dimensions such as the time or specific products like the LPIS IDs or the indices such as NDVI and things like that. So we are talking about a multi-dimensional arrays that you can slice and take whatever information is crucial for you. In this way, we can organize better the data, we can simplify the data access, and of course, the big keys here, the key here is the decrease of time complexity regarding all the processes that take place on the back end. So in this way, we can generate and we can simplify the process of generating analytics. We can store various data sets that are geo-referenced. We can either save satellite data or other meteorological data or data coming from Copernicus services. The key here is to be geo-referenced. And of course, all these things lead to the creation of better feature spaces for feeding our AI pipelines. The DataCube solution that we have implemented is hosted on ClearDias on a very powerful virtual machine, and we have created automated and scheduled pipelines that harvest Sentinel-1 and Sentinel-2 satellite data. We pre-process this data, and finally we index, we save this data and their metadata into our DataCube. Currently, we are hosting 3+ years of data for 2 countries at national scale. And these data are automatically populated with the new satellite products that are provided by the hubs. Let's move on to our first section, which are the geospatial analytics. This is just an introduction of why these analytics are so important and why we are talking about analytics all the time. As we have entered the era of big data, it's very important to unlock the power of big data, to unlock all this knowledge and information that may come up from this kind of data in order to enhance the decision-making process. This is very important in every scientific sector. However, and especially for the Earth observation data, it's very difficult to store, manage, process, and visualize all these things in order to gain and to extract useful information and knowledge based on traditional approaches. And thus, we have implemented this architecture that I was talking before. Based on this architecture, we have created some functionalities. we are going to present here some of them and to see how these functionalities are going to help users for the decision-making process. First of all, we have the temporal statistics over an area. User can easily ask for data for a specific area or for a specific parcel. Thus, it can be either pixel-based or parcel-based. And all this data, all these statistics can be plotted in a timeline. And this timeline can reveal many useful information. For example, you can see here a monthly, the image of a parcel over a year by month, and we have keep only the median of the month, the median value of each pixel for a month, in order to be as clear as possible due to the clouds. And you can see here the evolution of the crop phenology, which is very helpful because this specific example showcase a false declaration. The algorithms that the AI algorithms have created an alert for this specific parcel. This is a false declared parcel, and we can validate these results by the visualization. You can see here that the crop phenology evolution is different from the one that the crop should have based on the declaration, and thus we can validate the decision of the algorithm. This is the idea, to make a stronger validation based on this tool. So we can plot anything, any index we want, and in any time period we want. Except from this, we can take aggregated values for each parcel, and these aggregated values can be filtered, interpolated, resummed, and smoothed over the time. Why we have the need to do this process? Because many times, and especially in ENVISION for the Lithuania pilot case, we have many missing values due to clouds and shadows. So we need to interpolate and to filter out these outliers and these missing values. So except from the filling out from the interpolation, we can also apply smoothing functionalities in order to eliminate noise that can take place in our time series procedure. So by doing this smoothing process, we can identify easier any possible patterns and reveal any possible trends throughout the years. And this is very important because you have the aggregate value of the parcel, getting this value from only the clear pixels or the interpolated pixels. Moving on to the index anomalies. Generally, index anomaly means to provide a measure. For example, the NDVI standard anomaly provide a measure of vegetation health related to a long-term average condition. And these indices, these standardized anomalies, can be used to monitor areas where vegetation may be stressed and as a proxy for several things, such as a potential drought. So we can easily create this graph that represents index anomaly in order to detect some threats we can have in a specific area. Moving on to other functionalities, we starting from the results that we take from the backend processes, the machine learning processes, we populate a database which is per parcel. We have rows per parcel, and we store the results per parcel into a database. And these results come back to the cube. So it's a back and forth communication with the data cube. And this opens the room to complex queries. For example, show me all the misclassified or the false declarations for a specific crop type, or give me the crop types for a specific area to see what's happening here, what's the majority of the crops there. So we can make complex queries, and based on these queries, you get back all the information regarding the parcel, and combined alongside with the previous functionalities, you can make a very powerful analysis that enhances the validation decision-making process. In the end, you have a country-specific knowledge base for CAP monitor specifically. And this is a very important thing that you could have over the years in order to extract knowledge of what is happening in a specific area. That's all for the functionalities. Moving on to some specific services we have developed based also on the products and values that have been stored into the data cube. We have the minimum soil cover, the GAG4 of the current CAP demands that the identification, I'm sorry, of soil cover during specific months over the year. For example, Cyprus must be checked for 2 months, January and February. And in order to achieve this, we start by taking the average slope for each parcel from a digital elevation model. And we apply a very powerful thresholding algorithm. This has nothing to do with machine learning, but a very powerful thresholding algorithm which the geospatial soil sensing system uses. And according to this, we calculate several indices such as the NDVI, the NBR, the difference between some specific bands. And based on this algorithm, we end up to create soil masks in order to identify the percentage of bare soil into its parcel. Based on this percentage, we end up to have a final decision for the specific GAG rule. To extend this soil cover algorithm, we make also a runoff risk assessments, which is related to GAG1 rule and aims at the reduction of water pollution in specific areas, taking into account the proximity of the closest water surface. So based on this need, we have exploited the Russell model, which is a very strong model based on specific factors like the rainfall, the slope length, the vegetation cover, and other factors too. And we have made a more sophisticated approach. We take also into account the orientation of each parcel in order to label this parcel based on some rules that you can find here in this table. And also I mention again the orientation of the parcel in order to label the parcel and to give a risk factor for runoff assessment. The next service is related to stubble burn identification. This is a very important service for the paying agencies because it can monitor GAG6 rule, and this is a practice. The burning practice is almost never declared, so it's important for the paying agencies to know about this specific practice. Here, especially for the Cyprus, because the size of this parcel is very small, we use the pixel-based approach using the differential NBR index. And in order to apply it in all over the country, we have used sliding windows for national scale coverage, I said, and we take pair of images. For example, we take the image in time instance T and the next one also, or the T+2 image, 2 acquisitions after, and we check this pair of images. We calculate the differential NBR between these two these two images in order to extract the burn ratio for pixels falling into each parcel along with burn severity. You can see here in a screenshot that we identify the drops of NBR and the also when we have a specific threshold for the DNBR method here. And we identify this kind of drops in order to extract a result. I'm sorry for the baby on the back end. So moving to the next service is Natura 2000 hotspot detection. In the same way as we did in the stubble burning, we try to identify drops, but now we are using the NDVI index. Here we have an extra step because first of all, what we mean by Natura 2000 hotspot detection, there is a network of protected areas that you are not able to make any activities inside these areas, and we try to detect any illegal activities. But we exclude some parcels that are declared from the LPIS system inside these areas, and we exclude them from our analysis. So we try to find any other activities inside these regions based on the NDVI index and the drops such as the previous screenshot. Okay, these are all the functionalities in the service, but how can we access them? First of all, we have the ENVISION platform that has been developed and is up and running, where you can see for each parcel some statistics, some plots, some graphs, but beyond this in a platform, we have also developed an API service on which the users can make some specific requests based on certain parameters. So the users can ask, can construct a URL that consists of the parcel ID, the minimum cloud-free coverage, the index that they want to calculate, for example, the NDVI or the NDWI. There are a series of index, more than 10 index that can be asked from the users, the time range, starting date and end date, and the buffer zone, which means how many meters around the parcel you want the visualization to take place. So you can see the form of the URL, and the result of this request is a plot that you can see what's happening for this specific index and for this specific parcels throughout the time that you have, the time range that the user has set up. Except from this plot, users can take also an aggregated graph of this index, so they can take back the mean and the STD values of this specific index. But it is nowadays, because we make our own analysis, many times we want to harvest, to retrieve all the data in a raw format. I mean, maybe the data science does not want the pre-processed data that we offer, but they may want to get the raw data in order to make their own analysis. Thus, we are currently developing. It's in a staging. It's in a staging format. We have also developed a second API service that user can ask the raw data that are stored in the data cube, and they can get them back via XArrays, which is a very powerful data structure in order to handle multi-dimensional data. This service has been developed via the XPublish library, which utilizes on the back end FastAPI and Dask. Dask is a library that can efficiently handle many and large data set and enable also parallel processing. So users can retrieve data in the format that you can see in the screenshot here. You have many dimensions and you get the real value of the pixels. Last but not least, I've also developed a web application which is called the Data Cab, and is similar to the previous APIs, but it has an extra parameter, which is the street level images. So it offers the users the visualization that we talked before on the first API service, along with street level image. So the users have one more parameter in order to enhance the inspection of crop classification and grasslands mold results, which have been stored in the database, and the application retrieves them in order to enable the inspection process from the decision makers. That's all from me. Thank you very much for your interest.
Thank you, Thanasis. So I suppose we can pass to the last presentation for the day in the cultivated crop type maps by Jason.
Hello again. Marisa, can you use my screen again?
Yes, yes.
Okay, perfect. So here we have the maps product. This product is based on the creation of multi-temporal crop type maps, which are developed using the available Sentinel-2 images and Sentinel-1 images as well. These maps are based on well-tested from the literature machine learning and deep learning models, and are created for each acquisition, each novel acquisition individually. So we have new crop type map for every batch, let's say, of new Sentinel acquisitions. Our pilot cases are the Lithuania, which is a quite large territory, and we have the challenge of national scale results. And Cyprus, which has the problem of very small parcels. As I said earlier, the products are at national scale level and are developed on parcel or can be developed on parcel or pixel-based as well. Moreover, regardless the Sentinel-2 batch that we have to our disposal, we are creating the NDVI, the NDWI, or more vegetation index in order to enhance our results. Exploiting these crop type maps, we are developing some extra Earth observation services. The first one is the smart sampling in order to assist the on-the-spot checks expectations, which is essentially a traffic-like system that is based on the confidence provided from the crop type maps in order to identify the most confident misclassifications and pinpoint to the users the cases that we are more sure that are declared wrong. And we have the secondary crop diversification compliance maps, which is a product that is taking into account the Green 1 set of rules and the declarations of the farmer as well, the LPIS, in order to see if the cases match or not with the regulations of these policies. First case is Lithuania, which is quite large. For Lithuania, we have created taxonomy levels in order to improve our results and provide most confident cases. So we have created a taxonomy tree for the different crops. And we can see the distribution of this territory, which is essentially are grasslands and cereals. We are creating dynamic crop type maps for every new acquisition, and we have into account the amount of 14 Sentinel-2 tiles and 4 Sentinel-1 tiles in Sentinel-1 orbits in order to create our maps. For Lithuania case, we are using random forest model, and here we can see some visualization of the different crops, different crop phenology signatures, and as we can see, the distinction between them is becoming more clear essentially after summer. Which is something that tell us to expect higher results as long the cultivation periods move on. Using our algorithms, we are able we are able to locate cases that are declared wrong and essentially match the signature provided from the visual indices to the most characteristic phenology signature of the crops, and showcase cases that have been declared wrong. Essentially, especially for Lithuania, it's very good that we have a very low percentage of wrong declarations. So we are taking that into account. We are in the current declarations of we are training our routines of the declaration of the current cultivation period in order to provide our maps, our crop type maps. As we can see some preliminary results, the accuracy is quite high, almost 19%, and it's quite good for the majority of crops. The F-score and the performance of each crop individually is becoming higher as the cultivation period is moving on, and the confidence intervals, the predictions confidence of our routines are becoming higher and higher through cultivation period, and as well more sentinel images are included into our feature space. Moreover, we have developed our smart sampling routine that is taking into account the confidence intervals of the previous crop type maps and the current crop type map in order to showcase the most confident misclassifications, the most confident disagreement between the prediction and the declarations, actually. So we can see that the percentage, the amount of the high risk cases that we are very confident that are declared wrong is becoming smaller as the cultivation period move on, and the precision of the maps are becoming higher as well the recall. So some qualitative analysis, some qualitative description here. We can see in some qualitative example here, we can see that the high risk cases are becoming less and less as the cultivation period moving on, and the precision is becoming higher. At the end, we are able to indicate to the pilot case some cases, some individual cases that we are very confident that are declared wrong, and in the continuous, the respective paying agencies can design their own checking campaigns with higher performance. Now, case of Cyprus. For the case of Cyprus, we have as well create some hierarchical taxonomy, some taxonomic trees in order to provide some better results. As we can see, case of Cyprus is mostly characterized from cases of fallows and cereals, and some the case of Cyprus has the uniqueness that the percentage of wrongly declarations are quite high, and mostly are cases of these are cases of fallows. Especially this happens because the farmers are either omit to change their declarations form, the crop code of the current year, or intentionally provide the wrong label in order to agree with some substitute regulations, for example. For example, here we can see some cases that have been declared as fallow cases, but are obviously something other, a cereal, for example. The fallow land cases are cases that are not having any extra activity during the cultivation period, except some very short period. And as we can see, are very unique, since they have very different spatially allocation of the vegetation. Also, in the case of phallus, are included cases of very sparse trees, very sparse tree cultivations. Here we made analysis in order to allocate, for example, with some unsupervised machine learning routines, each individual crop code to some category. As we can see, we have created 4 very characteristic categories in order to allocate, for example, the different crop categories. For example, we can see for the cereals like barley and triticale, the characteristic or maybe some of the green. For the trees are the purple one, for the vineyards are the red one, and the grasslands the green, for example. As we can see for the case of phallus now, these cases are equally distributed among different groups. So this is a clear indication that we have a high percentage of wrong declarations. As we can see also from the plot here, we have very, very different signatures inside our fallow case dataset. So somehow we have to deal with this uniqueness. Moreover, in case of Cyprus, has the problem of very small areas. As a result, we have pixels actually that are belonging to more than one parcels, to more than one fields. And we have multiple cultivations that are all polycultures. Actually, these are cases that have been declared as one field, but obviously there are more crop types cultivated inside these areas. Or another problem is the very intense ground vegetations on permanent cultivations. The grass, for example, existing on the bottom, as we can see, is very, very intense. Case of Cyprus has also greenhouses that are not separated in the declarations. So we have cases that are temporary greenhouses or permanent greenhouses, and these are mostly vegetables. And somehow we have to distinguish these cases between them, since undoubtedly the phenology signatures cannot be similar. So we have created maps for Cyprus as well, using 2 Sentinel-2 tiles and 2 Sentinel-1 relative orbits. The results for Cyprus have been provided on a pixel level now, since we have the issue of small parcels, in order to enhance our performance. Moreover, in order to exploit the different hierarchical levels predictions, we have created some subroutines, actually a total pipeline composed for a very sophisticated composed from more sophisticated subroutines. In a few words, we are making predictions on higher level of taxonomy. For example, in the level of cereals or in the level of trees, in order to distinguish between them, something that is much easier. And then we are using these predictions in the feature space of the higher level discrimination, for example, the cereals between them, in order to make better our predictions. Something that I need to show here, for example, is that cases, for example, of barley or triticale or I don't know, soft wheat, cases that are wheat, that are cereals, are have very similar phenologies. So it's something that is a challenge for us to distinguish between them. The results now for case of Cyprus. As we can see, for the lower level of discrimination, the higher level taxonomy, no, the opposite, the lower level of taxonomy, the higher level of discrimination, the accuracy is not that good, since we have very low percentages of precision between for case of soft wheat or other cereals, something that is owed to the inability of the algorithm to distinguish between the cereals. As we can see, for example, for the matrices here, soft wheat or other cereals are always confused between them. On a higher level of taxonomy, the case is a bit better, and we can have a higher level of performance and distinguish better between the different situations. So how we can deal with that? For the future, we are planning to enhance our results. And the way to do that is to use more sophisticated deep learning models in order to take into account this and exploit the spatial distribution of the fields. So we will use some computer vision approaches for that task. Also, it is important to distinguish between homogeneous and heterogeneous fields and make some fields boundaries delineation, for example. As we can see, in the same field, they coexist more than one cultivations. Something that is for sure one reason that we don't have that high degree of accuracy. Another thing to do, since we have a high level of false declaration, is to train on previous years' validated data sets. So we will use validations from some previous cultivation periods in order to train our routines, and we will use these models for the current cultivation periods. That way, we can also cope better with the early warning, early classification results. All that will be done under the continuous communication with the paying agency of Cyprus, CAPO, in order to hear about them, how we are going and how they think we can move on. Since we have very good level of communications, and they are always very welcome to work with us and provide us some indications. In total, we have made parcel-wise or pixel-wise machine learning routines in order to create time series that will provide that will be included in a future space and we can create the crop type maps for the individual scenarios. We have two individual scenarios of Lithuania and Cyprus. Each scenario has its own problems and its own peculiarities. So, for example, in case of Lithuania, we have frequent cloud coverage, something that we are trying to solve with the parallel usage of Sentinel-1 and Sentinel-2 imagery. And on the other hand, in case of Cyprus, we have a small and narrow shaped parcel or higher percentage of false declarations. These unique cases can lead the way to create widely applicable solutions that we can apply, we can implement to other countries as well. Moreover, where there is nothing we can do, when the accuracy is small, we use our improved smart sampling algorithms, and we are using auxiliary routines in order to decide on the risk of the false declaration and provide some more precise results. In addition, a traffic light system can assist on the planning of the campaigns and the reductions of their cost. Also, early results can handle cases of disagreements between farmers and the respective paying agencies, and the results can be used in order to provide some greening one compliance map. Thank you very much for your attention.
Thank you, Jason. We are a bit we are actually over time. So maybe we have one or two pressing questions if there are. And of course, if there are any further questions, you can find Marisa's email on the invitation, so you can contact us through that email. So are there any questions?
I don't see any raised hands or something.
Okay, I see. Okay. So I see some people have to leave. So if there are no questions, again, you can find contact email on the invitation. We'll be glad to answer any further questions. So Marisa, should we close the webinar?
Yeah, sure. Thank you all for your attendance. And yeah, as Vasilis mentioned, if any questions, just drop us a line or contact us through the social media, etc. And we're happy to have a call with you. Thank you all very much.
Thank you. Bye-bye.